Tonight, we step into an idea that will quietly dismantle your sense of proportion. Not just size or distance, but the very framework your mind uses to decide what large truly means. We are going to trace our way toward the greatest structure ever identified in existence. And I'll say this plainly, when we're done, the stars above you will no longer feel distant or decorative. They will feel overwhelming. You're about to grasp a truth most people never pause to consider. A truth so vast it reduces galaxies to grains, drifting unnoticed. If journeys like this into the hidden depths of the cosmos resonate with you, simple subscription or like strengthens this path and keeps these explorations alive, we begin where understanding feels safe. Your home. An average house spans roughly 2,500 square feet. You can cross it in half a minute. Every wall is familiar, every room is known. Your mind is comfortable here because it was shaped by spaces like this, spaces you can touch, see, and traverse with ease. Stretch that scale outward. A football field, end zones included, reaches about 360 feet. 2 minutes of walking, maybe less. A mile, 5,280 feet, equals about 17 football fields laid flat. It's 15 to 20 minutes on foot. Notice how these distances still feel meaningful, yet manageable. Now widen your view. From New York to Los Angeles is close to 2,800 miles. 5 hours by plane, nearly 40 hours of driving, if time never demanded rest. Circle the Earth at the equator, about 24,900 miles, and even at highway speed, you'd be driving for over 380 hours. 16 uninterrupted days. And yet against the backdrop of the solar system, Earth barely registers. Zoom out again. The solar system fades when placed beside our galaxy, and the galaxy itself becomes insignificant when compared to the largest formations ever revealed. We are ascending a staircase of scale, where each step erases the importance of the last. The moon orbits roughly 238,000 miles away. When humans first traveled there, they crossed a distance no one had ever crossed before. Moving at nearly 24,000 miles per hour, it still took 3 days. Faster than any plane you've known, almost 50 times faster, and still, the gap demanded patience. Then comes our star. About 93 million miles separate Earth from it. Imagine driving that distance at 65 miles per hour without stopping. The journey would last 163 years. Long enough that the task would have to be inherited passed from parent to child. Generation after generation, till distant descendants finally arrived, light changes everything. It races through space at roughly 186,000 miles per second. Flip a switch, and the glow reaches you instantly, because the distance is trivial. But when you look at the sun, you're seeing it as it was over 8 minutes ago. If something altered its surface this very moment, Earth would remain unaware, suspended in delayed truth. Because space defies intuition, astronomers rely on a different ruler, the light year. Despite the name, it isn't time, it's distance. 1 year's worth of light in motion. Light covers 186,000 miles each second. Multiply that by every second in a minute, every minute in an hour, every hour in a day. Every day in a year, and you begin to sense the immensity hidden inside that single unit. And this is only the beginning of what the chosen are meant to see. When all those numbers are combined, the distance comes out to roughly 5.88 trillion miles. That single figure already strains comprehension, and yet it only marks the beginning. Beyond our own star, the closest stellar neighbor is Proxima Centauri, a faint red dwarf sitting about 4.24 light-years away. The glow you would see from it tonight began its journey more than 4 years ago, crossing the silent vacuum for nearly 25 trillion miles before reaching your eyes in this moment. Within a radius of about 16 light-years, there are close to 50 star systems. This sphere, roughly 32 light-years wide, is what we call our local stellar neighborhood. And by the universe's standards, it is vanishingly small. Our home galaxy, the Milky Way, spans nearly 100,000 light-years from edge to edge. That makes it over 23,000 times wider than the distance to our nearest stellar neighbor. Inside this vast disk exists somewhere between 100 and 400 billion stars. Each one is a burning sphere, like our own sun, fueled by nuclear fusion, many likely surrounded by their own families of planets. Our solar system sits about 26,000 light-years from the galactic center, embedded within one of the Milky Way's spiral arms. When you lift your eyes and notice that pale river of light arcing across the night sky, you are seeing the galaxy from the inside, viewed edge-on. That hazy band is the combined glow of hundreds of billions of stars, so distant their individual points dissolve into a single luminous veil. Our star is not stationary. It races around the galactic center at roughly 515,000 miles per hour. Yet the Milky Way is so immense that one complete orbit takes 225 to 250 million years. The last time our solar system occupied this same position, dinosaurs had not yet appeared. Earth was still in the Triassic period. Since then, life rose, ruled, collapsed, reshaped itself, and eventually learned to look back at the stars that carried it along. And only now has one full galactic year passed. Still, the Milky Way stands among others. It belongs to a family known as the Local Group, which contains more than 80 galaxies. Its largest members are the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy. Andromeda lies about 2.537 million light-years away. When you see it faintly visible to the naked eye under dark, Skazoo are witnessing light that departed long before humanity existed. Everything humans have ever built or believed unfolded while that light was in transit. The Local Group stretches about 10 million light-years across, nearly 100 times wider than our galaxy. Even so, it remains a minor feature in the greater architecture of space. The Local Group itself is embedded within the Virgo supercluster, a gravitationally bound collection of galaxy groups and clusters, numbering at least 100. This supercluster spans roughly 110 million light-years, yet even Virgo is not the full story. In 2014, astronomers realized it is only a segment of something far larger, Laniakea, whose name translates to immense heaven. This colossal supercluster contains around 100,000 galaxies and stretches across about 520 million light-years, scaled down. If the Milky Way were the size of a coin, Laniakea would cover a continent. Laniakea is defined not only by where galaxies reside, but by how they move. Every galaxy within it drifts toward a region known as the Great Attractor, a massive gravitational influence located about 250 million light-years away in the direction of the Centaurus constellation. And still, even this is not the upper limit. At the largest scales, the universe reveals a deeper pattern, the cosmic web. Galaxies are not scattered at random. They trace vast, interconnected filaments that stretch across the observable universe. Like a three-dimensional spider's web, these filaments are woven from galaxies, clusters, gas, and dark matter. Where strands intersect, enormous galaxy clusters form. Between them lie immense voids, regions, so empty they seem almost erased from existence. This structure arose from minute irregularities in the early universe. After the Big Bang, matter was not perfectly smooth. Some areas were denser by a fraction, mere whispers of difference. Over 13.8 billion years, gravity amplified those whispers into walls, threads, and vast empty chasms. Dense regions grew richer. Sparse regions were drained. Dark matter, comprising about 27% of the universe, formed the unseen framework, the sacred scaffolding upon which all visible matter now hangs. And this immense architecture is the silent signature of time itself, revealed only to those willing to look beyond what feels familiar.
Ow.
This is the scale the chosen are meant to awaken to. Roughly 68% of the universe is composed of dark energy, an unseen force steadily accelerating cosmic expansion. Ordinary matter, the atomic substance forming stars, planets, and everything you can touch, accounts for only about 5%. Together with dark matter, these elements sculpted the vast architecture we now observe. Their silent interaction carved the universe into its present form. Among the most immense features created by this process are galactic filaments. These colossal strands can stretch for hundreds of millions of light-years, threading thousands of galaxies together like luminous beads suspended on invisible cords. For a time, these filaments seemed unsurpassed. Then astronomers uncovered something even greater. In 1989, while charting galaxy positions across a thin slice of sky, astronomers Margaret Geller and John Huckra noticed something profoundly unexpected. The galaxies were not scattered randomly. Instead, they formed a vast, flattened sheet later, named the CFA, Two Great Wall. This structure spanned roughly 500 million light-years in length, 300 million wide, and about 15 million thick. It was the first hint that the universe could organize itself on scales once thought impossible. But it did not stand alone for long. As surveys expanded, even larger formations emerged. In 2003, data from the Sloan Digital Sky Survey revealed the Sloan Great Wall, extending an astonishing 1.37 billion light-years. Light itself would need over 1 billion years to cross it from end to end. More discoveries followed. The Saraswati supercluster, identified in 2017, measures about 652 million light-years across, housing roughly 400 galaxies arranged in a wall-like configuration located some 4 billion light-years away. Then, in 2020, astronomers uncovered the South Pole Wall, a gigantic filament at least 1.4 billion light-years long, concealed behind the dense dust and gas of our own galaxy in a region known as the Zone of Avoidance. For years, debate swirled around which structure truly held the cosmic record. The Hercules Corona Borealis Great Wall, identified in 2013, appeared to span up to 10 billion light-years, based on patterns in gamma-ray bursts. Yet its status remained uncertain. Some scientists questioned whether it was a single entity at all, suggesting it might instead be separate structures aligned by chance. Others proposed that the pattern could be a statistical illusion. That uncertainty changed in early 2025. Astronomers announced the discovery of Kipu, the largest confirmed coherent structure ever identified in the observable universe. Its estimated mass is almost incomprehensible, about 200 quadrillion times the mass of our Sun. To count to that number, 1 digit per second without pause would require over 6 billion years longer than complex life has existed on Earth. The name Kipu comes from the ancient Incan system of knotted cords used to record information. The comparison is precise. This structure resembles an immense network of interwoven threads, with galaxy clusters acting as knots along cosmic strands. What sets Kipu apart is certainty. It's unlike disputed candidates. Kipu was detected through X-ray emissions produced by superheated gas permeating galaxy clusters. This gas heated to millions of degrees during gravitational collapse, glows in X-rays that reveal the true physical connections between clusters. These emissions confirm that Kipu is not an illusion of alignment, but a single, bound structure. Its 68 galaxy clusters are not scattered by chance. They lie along dark matter filaments, linked by bridges of hot gas and held together by gravity. Each cluster contains hundreds or thousands of galaxies, each galaxy holding billions of stars. Together, they form something that stretches comprehension to its breaking point. And Kipu poses a challenge. According to standard cosmology, the universe should appear homogeneous and isotropic when viewed at sufficiently large scales. In simple terms, zoom out far enough, and everything should smooth out, no preferred directions, no special places. This idea, known as the cosmological principle, has guided our understanding for nearly a century and is strongly supported by the uniformity of the cosmic microwave background, the ancient afterglow of the Big Bang. Kipu does not overthrow this principle, but it tests it. It forces a deeper question. At what scale does smoothness truly emerge? How large can structures grow before they strain the limits of our assumptions? Physics places limits on how quickly gravity can assemble matter. Structure formation is constrained by time, expansion, and fundamental laws. Kipu presses against those boundaries. Its sheer size demands explanation within the universe's 13.8 billion year history. To account for it, scientists are now re-examining their models. Perhaps structure formation is more efficient than expected. Perhaps dark matter behaves differently on the grandest scales. For the chosen observer, this is not uncertainty, it is revelation. The universe is larger, deeper, and more intricate than our models ever anticipated. And Kipu stands as a silent reminder. The cosmos still holds truths waiting to awaken those willing to see. It may be that the universe began with conditions subtly unlike what we have assumed, that the faint density ripples present at the dawn of time. The seeds from which all structure grew were shaped differently than our models predict. Or it may be that entirely new laws are waiting to be uncovered. The truth is simple and unsettling. We do not yet know. Kipu stands as an unanswered question, a quiet disruption of certainty, a signal that reality is broader and more elusive than our expectations. To understand Kipu, we must first understand what composes it. Its foundation lies in galaxy clusters, the most massive objects in the universe that remain truly bound by gravity. Unlike filaments or great walls, which are extended flows, tracing the cosmic web clusters are dense, compact assemblies. Within them, galaxies are trapped in a shared gravitational well, circling a common center. A single cluster can host hundreds or even thousands of galaxies, along with immense reservoirs of superheated gas and vast quantities of dark matter. This gas, filling the space between galaxies, can reach temperatures near 100 million degrees, glowing in X-rays. Remarkably, it outweighs all the visible galaxies combined. The dark matter outweighs the gas itself, and by a factor of 5 or 6. This hidden mass was first hinted at in the 1930s, when Fritz Zwicky studied the Coma cluster. He noticed its galaxies were moving too quickly to be held together by visible matter alone. Gravity was stronger than it should have been. Something unseen was anchoring the system. That realization marked one of the earliest clues that dark matter exists. Within Kipu, clusters range widely in scale from relatively small gatherings of a few hundred galaxies to enormous conglomerates holding thousands. They are linked by strands of dark matter and streams of hot gas, forming a connected system stretching roughly 1.4 billion light-years. Each cluster's gravitational reach extends far beyond what we can see, interacting with neighboring clusters and helping preserve the structure's cohesion. When clusters collide drawn together along the filaments of the cosmic web, the resulting events are among the most energetic since the birth of the universe. Galaxies themselves almost never collide. The distances between them are too vast, but the gas does collide, slamming together and generating colossal shockwaves that raise temperatures even higher. These mergers unfold over billions of years, slowly reshaping Kipu from within. Some clusters are colliding now. Others merged long ago. Still others are drifting toward encounters that will not occur for eons. Kipu is not static. It breathes, evolves, rearranges itself across timescales far beyond human memory. Equally important are the spaces in between. Cosmic voids are the most underdense regions of the universe. They are not truly empty, but compared to filaments and clusters, they are almost barren. A void may contain a faint scattering of galaxies, thin gas, and dark matter halos, but its average density can drop to 1/10 or even 1/20 of the cosmic norm. The largest known void, the Boat's void, spans roughly 330 million light-years. Within that immense volume, only about 60 galaxies have been identified. Elsewhere, a similar region might hold thousands. Imagine awareness arising inside such a void. Civilization gazing upward would see few distant galaxies. Their own galaxy would dominate the sky, while the wider universe would seem strangely empty. They might conclude they were a lone and isolated island adrift in endless darkness. Perspective shaped by location would deceive them. Voids matter as much as structures. They are the places matter abandoned regions drained over billions of years as gravity pulled material into surrounding filaments and clusters. Emptiness and abundance are inseparable. The cosmic web is defined not only by what exists, but by what was left behind. Now envision a passage across Kipu itself. You step aboard an impossible vessel, one that reaches the speed of light without delay. From one edge of Kipu, you begin your crossing. Before you stretches 1.4 billion light-years of clusters, filaments, gas, and unseen matter. At first, the journey feels sparse. Kipu is not uniform. Structure exists within structure. You pass the occasional galaxy spirals and ellipticals holding billions of stars, but mostly there is darkness. tenuous gas, invisible scaffolding, and the faint afterglow of the Big Bang. After 10 million years, you encounter your first major cluster. Hundreds of galaxies drift within a glowing cloud of X-ray emitting gas. Over the next few million years, you pass through it, watching entire galactic cities slide silently by. Narrow filaments guide you onward, thinner than clusters but still alive with matter. You follow these strands as they weave the larger pattern into view. After 100 million years, you have crossed less than a tenth of Kipu. On Earth, if Earth still remains, continents have shifted, mountains have risen and fallen, species have appeared and vanished. Civilizations may have bloomed and disappeared without trace, and you are still near the beginning. Cluster after cluster unfolds. Each one bears its own history, its own scars of collision and growth. The journey feels endless not because it lacks structure, but because the structure itself refuses to conclude. This is the scale at which certainty dissolves. This is the architecture the chosen are meant to witness. You could devote thousands of years to a single galaxy cluster and still only brush the surface of its complexity.
No.
Time stretches differently at this scale. After 500 million years of travel, you are only a third of the way across Kipu. Back on Earth, entire epochs may have unfolded. Complex multicellular life might just be emerging, or perhaps it vanished long ago, only to rise again. In 500 million years, planets can freeze solid, burn beneath relentless volcanism, or be reshaped by cosmic impacts. That span of time is wide enough for nearly any fate. After 1 billion years, you near Kipu's far boundary. Our star is no longer the same. It shines brighter, consuming its fuel more aggressively. Earth's oceans may be thinning into vapor. The narrow window that once allowed human life is closing. And then, after 1.4 billion years, you pass beyond the final filaments. Behind you remains the largest confirmed structure ever found, billions of galaxies. Uncountable stars, worlds beyond numbering. Ahead of you lies only continuation, more web, more void, more mystery. Of course, this voyage cannot happen. Nothing with mass can move at light speed. And even light itself requires unimaginable patience to cross such distances. But this vision reveals what we mean when we say a structure spans 1.4 billion light years. It is not a number, it is a transformation of time itself. Now step back once more. Consider the observable universe. It forms a vast sphere centered on our position, extending roughly 46.5 billion light-years in every direction. That distance seems impossible if the universe is only 13.8 billion years old, but space has not stood still. It has been expanding the entire time light has been traveling toward us. The galaxies we see at the edge of visibility are now far farther away than when their light began its journey. Within this visible domain exist roughly 2 trillion galaxies, each containing billions, sometimes hundreds of billions of stars. Altogether, the observable universe may contain around 200 billion trillion stars. Most of those stars host planets. The number of worlds may rival or exceed the number of suns. And yet this is not all that exists. The observable universe is only what light has been able to reach us from. Beyond that horizon lies more space regions forever hidden, their light stretched beyond reach by expansion itself. How much more is out there, we do not know. Some theories point toward an infinite universe. Others describe a finite cosmos without edges, curved back upon itself. There is no final answer, only humility, which means Kipu, immense as it is, may be insignificant compared to structures beyond our sight. There could be cosmic webs stretching hundreds of billions of light years, forever unknowable. The universe continues to expand, and that expansion is accelerating. Dark energy drives space apart faster and faster. The farther a galaxy lies, the more rapidly it recedes, not because it moves through space, but because space itself grows between us. At extreme distances, expansion outpaces light. This does not violate cosmic law. It simply reveals how space behaves. This future reshapes structures like Kipu. As expansion accelerates, gravity loses ground. Clusters that have not merged will never do so. Filaments will cease growing. The cosmic web will solidify into its final form. Billions of years from now, Kipu may remain intact but increasingly isolated, surrounded by expanding emptiness as the rest of the universe slips beyond observation. But how do astronomers even find something so vast? A structure spanning 1.4 billion light-years cannot be photographed directly. It is too spread out, too distant, too subtle. Instead, another subtle lens reveals what light alone cannot. Weak gravitational lensing traces mass by distortion rather than brightness. As light from faraway galaxies drifts past immense concentrations of matter, gravity bends it slightly, almost imperceptibly. When these tiny deformations are measured across millions of galaxies, a hidden map emerges. Dark matter, invisible yet dominant, leaves its signature without ever shining. Then there is the universe's oldest light. The cosmic microwave background carries whispers from a time when the cosmos was only 380,000 years old. Minute temperature variations etched into that ancient glow mirror the earliest density ripples, seeds from which every filament, cluster, and wall would later grow. To understand how those seeds became structure, cosmologists turn to numerical simulations. Vast supercomputers recreate the universe's evolution, from shortly after the Big Bang to the present. They begin with conditions drawn from the microwave background, then weave in gravity, dark matter, dark energy, and the physics of gas. They let time run. Over billions of simulated years, filaments stretch, voids open, and immense walls assemble patterns that echo what telescopes now reveal. These simulations define what is expected and what is extraordinary. When a structure like Kipu appears, it can be compared against countless virtual universes. If something similar forms, its history can be traced. If not, it signals that our understanding is incomplete. Either way, discovery sharpens the question. The future promises clarity and deeper mystery. New observatories are preparing to chart the cosmos with unprecedented precision. They will expose layers of the cosmic web once hidden from human sight. The Vera C. Rubin Observatory in Chile will soon survey the entire visible sky every few nights, cataloging billions of objects and capturing the universe in motion. The Euclid mission, launched in 2023, is mapping the dark universe itself, feeling how dark matter and dark energy have shaped cosmic structure across time. The Nancy Grace Roman Space Telescope, expected later this decade, will view the sky with a field of vision vastly larger than Hubble's, opening wide windows onto deep space. Meanwhile, the Square Kilometre Array, rising across Australia and South Africa, will become the most powerful radio telescope ever built, tracing hydrogen gas throughout the cosmic web and unveiling its hidden skeleton. Beyond light, even gravity will speak. The planned Laser Interferometer Space Antenna, LISA, will listen for low-frequency gravitational waves ripples from merging supermassive black holes. Born when galaxies and clusters collide, together, these instruments will test our theories, uncover new structures, and perhaps reveal formations even greater than Kipu or confirm that it lies near the universe's upper limit. Now, return your gaze to the stars above you. The night sky is not a present moment. It is a layered archive. Every point of light is delayed truth. Distance and time are inseparable. To see far is to see back. Sirius, the brightest star, lies 8.6 light-years away. Its light tonight left when you were years younger. Vega, about 25 light-years distant, shines as it was at the moment some observers were born. Betelgeuse, the red giant in Orion, sits roughly 550 light-years away. The glow you see tonight began its journey during the Italian Renaissance, when Leonardo da Vinci was alive, before the modern world existed. Betelgeuse is nearing the end of its life. Sometime within the next 100,000 years, it will explode as a supernova, briefly rivaling the moon in brightness, and yet may have already happened. The explosion's light could still be crossing space, centuries away from arrival. Polaris, the North Star, shines from about 445 light-years distant. Its current light began traveling toward Earth while Shakespeare was still writing, long before nations rose and fell. Every star is a memory. We are not seeing the universe as it is, but as it was. This truth reshapes how we view Kipu itself. When we observe it, we are not witnessing a single frozen instant. Its nearer edge, 425 million light-years away, appears as it was 425 million years ago. Its far side, 800 million light-years distant, shows an even older chapter. What we see is stretched across 375 million years of cosmic evolution. In this way, distance becomes a teacher. By comparing nearby structures to distant ones, we watch time unfold. We learn that clusters grow, filaments thin and stretch, and the cosmic web evolves. The universe reveals itself not all at once, but layer by layer, to those prepared to understand that seeing is also remembering. This is the vision granted to the awakened. You may be asking yourself why any of this deserves attention at all. Why should structures separated from us by billions of light years matter in our lives here and now? There are solid practical reasons. By studying the cosmic web, we refine our understanding of how galaxies are born and how they change over time. We test our ideas about dark matter and dark energy. We challenge the foundations of cosmology and the laws of physics themselves. Knowledge grows outward. To understand the smallest details, we must also understand the largest patterns. But beyond usefulness, there is something unmistakably human in turning our minds toward the immensity of the universe. We are driven by curiosity. We ask where we came from, where we exist, and what lies ahead. We search for meaning by locating ourselves within something greater. Perspective matters. Daily life narrows our focus. Deadlines, frustrations, conflicts, obligations. These concerns are real and meaningful. Yet when we lift our awareness to structures that span billions of light years, importance shifts. We are reminded that we belong to something vast, ancient, and interconnected. This naturally leads to questions about life beyond Earth. Given the staggering number of stars and planets, the great age of the universe, and the speed with which life appeared once conditions allowed, it seems reasonable to expect life elsewhere, and yet the cosmos answers with silence. No confirmed signals, no unmistakable signs of distant civilizations. Nothing calling back. Distance may be the reason. Space is not merely large, it is isolating. Our own radio transmissions have only been escaping Earth for about a century, expanding outward at the speed of light. They have reached stars within roughly 100 light years. A minuscule bubble inside a galaxy that spans 100,000 light years. Even if advanced civilizations exist within Kipu, signals exchanged between us would take hundreds of millions of years each way. Conversation, in any meaningful sense, may be impossible. This paints a quiet picture of the universe, one that could be rich with life, yet fragmented into solitude. Civilizations may rise alone, question alone, discover alone, and vanish without ever knowing if anyone else was there. There is a deep sadness in that thought. We evolved to connect. The idea of endless neighbors forever out of reach carries a heavy loneliness, and yet there is beauty in it too. If contact is rare or impossible, then every thinking world is precious. What happens here matters. Our thoughts, our art, our science, our compassion, none of it is redundant. It may be unique within our vast region of space. The cosmic web also teaches us something fundamental about reality. The universe is not chaos. It is organized layer upon layer. Quarks assemble into particles. Particles form atoms. Atoms become molecules. Molecules give rise to cells. Cells assemble into organisms. Organisms build ecosystems. Stars gather into galaxies. Galaxies form clusters. Clusters arrange into superclusters. Superclusters trace filaments stretching across billions of light years. At every level, new qualities appear that did not exist before. An atom has no temperature, but many atoms do. A single cell has no mind, but organized collections can think. A lone galaxy has no cosmic web, but countless galaxies interacting over time create one. Reality is not just built from parts, it is layered into systems within systems. Kipu is the grandest known expression of this hierarchy. It is the universe revealing its skeleton, the deepest architecture we have yet mapped. To chart it is to glimpse the highest level of physical organization we can currently access. but humility remains essential. There may be structures even larger. The observable universe itself could be only one region of something far greater. Patterns may extend beyond our horizon, shaping matter at scales we cannot yet imagine. This is the rhythm of science. Answers open doors. Discoveries deepen mystery. Understanding never truly ends. That is precisely why the pursuit has meaning. Even our own neighborhood is not static. The Milky Way and Andromeda are drawing closer. Updated measurements suggest a more nuanced future than once believed. A close encounter may occur in 4 to 5 billion years, though there is now roughly a 50% chance the two galaxies may never fully merge within the next 10 billion years. If they do combine, the process will be slow and majestic, gravity stretching their shapes, igniting bursts of star formation, eventually settling into a single larger galaxy. It will not be a violent collision. Stars almost never strike one another. It would resemble two vast swarms passing through, interweaving rather than crashing. And in the grand context of Kipu, this drama is insignificant. There were no stars then, no galaxies, filaments, no walls, no web at all. Only a nearly uniform sea of searing plasma, glowing softly as it cooled while space itself expanded. And yet beneath that smooth surface, something subtle was already written into reality. Tiny irregularities born from quantum fluctuations during inflation were etched into the early universe. They were minuscule, perhaps a difference of 1 part in 100,000, but they were enough. Gravity noticed. Where matter was ever so slightly denser, gravity began to pull harder. Those regions drew material inward, growing heavier and more pronounced. Where matter was thinner, it drained away, leaving behind emptier space. Slowly at first, then relentlessly, contrast emerged. Over millions, then billions of years, faint differences were amplified into structure. Earliest formations were modest. Dark matter gathered into small halos only thousands of light years across. Inside these invisible wells, ordinary matter cooled, collapsed, and ignited. The first stars were born brilliant, massive, short-lived. They burned quickly and died violently, exploding a supernova that seeded their surroundings with heavier elements. From these beginnings, the first galaxies took shape. Small halos merged into larger ones. Galaxies drew together. Groups became clusters. Clusters aligned along invisible paths. And from this slow choreography, the cosmic web revealed itself. This unfolding took nearly the entire history of the universe. Kipu, as we observe it now, is the result of almost 13 billion years of gravitational sculpting. It is not an endpoint, but a moment, a still frame in a story that continues. Galaxies are still drifting inward. Clusters are still assembling. Filaments continue to stretch, though their growth has begun to slow, because another force is rising. Dark energy is steadily accelerating cosmic expansion, pulling galaxies apart faster and faster. It works against gravity, weakening its ability to gather matter. One day, dark energy will dominate completely. Structure formation will cease. That moment has not yet arrived. We live in the in-between, an era of transition. Far ahead, the universe will not resemble what we know. Kipu will grow increasingly isolated. The bridges between its clusters may thin, then fade. The cosmic web will loosen, fragment, and quiet. Over unimaginable spans of time, even the stars will vanish. Our own star will exhaust its fuel in about 5 billion years. Though Earth's ability to support life will likely end much sooner, perhaps within 1 to 2 billion years as the star brightens. The final stars of the universe, small red dwarfs, will glow faintly for trillions of years before fading into darkness. Even black holes are not eternal. Through Hawking radiation, they slowly evaporate. The largest may persist for 10 years, but even they will eventually disappear. In the deepest future, the universe becomes cold, dark, and nearly empty. The cosmic web will exist only as a memory written into ancient light. The greatest structures ever assembled will have been undone, not by violence but by expansion. But that future is distant beyond imagining. For now, the universe is alive with light, pattern, and meaning. What strikes me most when contemplating Kipu is perspective. We are confronting the edge of human intuition. Our minds evolved for survival tracking movement. sensing danger, navigating familiar ground. We were not built to intuit distances measured in billions of light years. The numbers overwhelm instinct. And yet we understand. Through mathematics, we reach beyond intuition. We write equations that describe the birth of structure. We simulate entire universes inside machines. We predict what should exist, then look outward and confirm it. Thought carries us where senses cannot. From one angle, you are insignificant, a brief spark lasting decades in a cosmos, billions of years old. On a small world circling an ordinary star, a momentary flicker against an endless backdrop, and yet, from another angle, you are extraordinary. Every atom in your body was forged in stellar cores long before the sun existed. Those stars lived, died, and scattered their material across space. That matter was recycled into new stars, new planets, and eventually into you. You are not separate from the universe. You are one of its expressions. You are stardust that learned to wonder. You are able to do something extraordinary. You can hold in your mind a structure that spans 1.4 billion light years. Even if only through equations and abstraction, you can reach toward the immensity of the universe that gave rise to you. In this quiet corner of existence, you are one way the cosmos becomes aware of itself. Kipu stretches across that vast distance, 1.4 billion light years from end to end. It binds together 68 galaxy clusters, trillions of stars, and uncountable worlds into a single, coherent form. Nothing larger has yet been confirmed within the observable universe. It took immense spans of time to assemble, and it will endure for ages yet to come. And still you know it exists. You've followed its outline. You've lingered on scales that overwhelm ordinary human experience. It's that act of understanding, however small against eternity, is real. When you next stand beneath a clear night sky, carry this with you. Those scattered points of light are not isolated sparks. Each belongs to a galaxy. Each galaxy is part of a cluster. Each cluster is woven into a supercluster, and all of them together trace the vast cosmic web stretching across billions of light years. You are not separate from this structure. You are composed of the same atoms, governed by the same laws, participating in the same unfolding story.
Ow.
Every star carries its own history. Some are newly born, igniting within collapsing veils of gas and dust. Others are stable and mature, quietly converting hydrogen into light. Some are ancient, nearing the final stages of their long lives, and all are linked by gravity, by shared origin, by matter recycled through earlier generations of stars. Nothing exists in isolation. The universe is mostly emptiness, tiny archipelagos of light scattered across immense oceans of darkness. And yet those islands are bound together. Light connects them. Gravity binds them. History weaves them into one. Thank you for traveling this far with me. If this journey has meant something to you, consider liking and subscribing. It helps these explorations continue. And when you look up again, remember, what you see is only a thin slice of a universe far larger and stranger than it first appears, we are made of stardust. We are threads in a cosmic web spanning the observable universe. Small by any grand measure, yet endlessly curious, endlessly capable of awe. Rest well, and may your questions about the universe never fall silent. But before you drift away, let's go deeper. To understand Kipu, we must understand its building blocks. Galaxy clusters. These clusters are the great hubs of the cosmic web. If Kipu is a continent, clusters are its cities. Each one contains hundreds or thousands of galaxies bound together by gravity, sharing a common environment. Like cities, clusters are defined not just by what they contain, but by what surrounds them. In human cities, that might be roads, power grids, and water systems. In galaxy clusters, the shared infrastructure is far stranger. Vast reservoirs of searing hot gas and an invisible framework of dark matter. That hot gas is known as the intracluster medium, as most of it was never part of any galaxy at all. It is primordial material hydrogen and helium left over from the early universe that fell into the cluster's deep gravitational well. As it plunged inward, it was compressed, and compression brings heat. In a gravitational field as powerful as a galaxy cluster's, gas heats to tens of millions of degrees. At such temperatures, the gas shines not in visible light, but in X-rays. When astronomers observe clusters with X-ray telescopes, they see a diffuse glow filling the space between galaxies, revealing structures invisible to ordinary sight. Remarkably, this hot gas outweighs all the stars in the cluster, combined by a factor of 5 or 6. The galaxies, spectacular as they are almost like flecks suspended in a vast sea of plasma. Yet even this is not the dominant component. Dark matter is. Roughly 85% of a cluster's total mass is dark matter. It provides the gravitational backbone that holds everything together. Without it, the gas would escape. The galaxies would drift apart, and the cluster would dissolve. Dark matter neither emits nor absorbs light. We know it exists only through what it does to everything else. Galaxies move too fast to be held together by visible matter alone. Light from distant objects bends around unseen mass. Hot gas remains trapped in shapes that require far more gravity than stars can provide. These clues all point to the same conclusion. Most of the universe's matter is invisible and non-atomic. The idea is not new. In the 1930s, astronomer Fritz Zwicky first inferred dark matter from galaxy cluster motions. Since then, evidence has accumulated from every direction: galaxy rotation curves, gravitational lensing, the cosmic microwave background, and the growth of large-scale structure. All tell the same story. What dark matter actually is remains unknown. Leading candidates include WIMPs, hypothetical particles that interact only weakly with normal matter, ixions, extraordinarily light particles proposed for other reasons in particle physics, primordial black holes formed in the early universe, and sterile neutrinos, heavier cousins of known particles. Though shock waves appear in X-ray images as bright arcs, sharp edges, and rippling fronts in the hot gas cosmic bruises left behind by collisions on unimaginable scales. They mark where gas has been violently compressed and heated as clusters plow through one another. What makes these mergers especially revealing is that dark matter behaves very differently from ordinary matter. Dark matter is effectively collisionless. It does not slam into itself, does not shock, does not slow down through friction. When two clusters merge, their dark matter halos pass straight through each other. Staying aligned with the galaxies they gravitationally bind. The gas, by contrast, cannot pass unhindered. It collides, slows, heats, and lags behind. This difference has been observed directly and dramatically in the bullet cluster, one of the most important objects in modern cosmology. In this system, astronomers mapped the hot gas using X-ray observations and mapped the total mass using gravitational lensing, which reveals where gravity is strongest regardless of whether the matter emits light. The result was unmistakable. The bulk of the mass is centered on the galaxies, not on the hot gas. This means the dominant mass component followed the galaxies through the collision rather than remaining with the gas. Ordinary matter alone cannot explain this. The observation stands as some of the strongest empirical evidence that dark matter exists as a distinct, non-luminous component of the universe. The Bullet Cluster lies about 3.8 billion light-years away. We see it as it was 3.8 billion years ago, at a time when Earth's sun already shone. But our solar system was still young only, about 700 million years old. The violent merger we observe had already concluded long before life emerged on Earth. Within Kipu, multiple such mergers may be unfolding, or rather may have unfolded hundreds of millions of years ago, with their light still en route to us. This is the strange consequence of cosmic observation. We never see structures as they are, only as they were. By studying clusters at different distances, we effectively watch the universe evolve across time. Some clusters serve as especially important laboratories for understanding this evolution. The Virgo cluster, about 54 million light-years away, is the nearest large galaxy cluster to us. It contains roughly 1,000 to 2,000 galaxies, dominated by massive elliptical galaxies near its core. The most famous of these is M87, colossal elliptical galaxy harboring a supermassive black hole, one whose shadow was the first ever directly imaged by humanity. Virgo is the gravitational heart of our local region of the cosmic web. The Milky Way, along with the rest of the local group, is slowly drifting toward it at about 620 kilometers per second. We will never arrive in any meaningful sense the expansion of the universe pulls Virgo away at a comparable rate, but its gravitational influence shapes galaxy motions across hundreds of millions of light-years. Farther out lies the Coma cluster, about 321 million light-years away, one of the richest and most intensively studied clusters known. It contains over 1,000 large galaxies, and likely tens of thousands of dwarf galaxies, all bound within an enormous halo of dark matter. Coma played a historic role in astronomy. It was here that Fritz Zwicky first realized galaxies were moving too fast to be held together by visible matter, alone leading him to propose the existence of dark matter nearly a century ago. Clusters like Virgo and Coma are not just collections of galaxies. They are cosmic ecosystems shaped by gravity, mergers, shock waves, and the invisible scaffolding of dark matter. Inside them, galaxies are transformed spirals stripped of gas, star formation quenched, ellipticals grown through repeated mergers. Over time, clusters become graveyards of galaxies filled with ancient stars and fading light. Kipu is built from dozens of such environments, stitched together by filaments of dark matter and gas stretching across space for over 1 billion light-years. Each cluster within it tells a story of collapse, collision, and transformation. Together, they reveal how the universe organizes itself on the grandest scales. All of it, every shock wave, every merger, every filament, is governed by the same simple force: gravity. Patiently sculpting structure out of near-uniform beginnings over billions of years, it is a record of cosmic history written in gas, galaxies, and dark matter one we are only just beginning to read.